Welcome to the capstone of your Pure 1 calculus journey, integration. If differentiation is the mathematical tool we use to break a function down to find its rate of change, integration is the process of building it back up. But it is much more than just anti-differentiation. It is a profound concept that allows us to calculate accumulated totals, most notably the exact geometric area enclosed by curved boundaries. This unit sits at the very peak of the syllabus. It relies heavily on your fluency with algebra, particularly your confidence with the laws of indices, and unlocks some of the highest tariff marks in Paper 1. We begin our journey with the abstract theory. How do we undo a derivative to find the original function? To integrate a standard polynomial term, you simply increase the power by 1 and then divide by that new power. However, because differentiating any constant number yields 0, reversing the process introduces an unknown constant of integration, which we call c. This represents an entire family of parallel curves that all share the exact same gradient function. Forgetting to write plus c at the end of an indefinite integral is the single most common way candidates lose their final accuracy mark.
Once your algebraic manipulation is secure, we introduce boundaries to create definite integrals. By evaluating your integrated function between a specific upper and lower limit, the unknown constant, c, cancels out entirely, leaving you with a precise numerical value. The Cambridge mark scheme is highly structured here. There is almost always a dependent method mark specifically for showing the substitution of your upper limit minus your lower limit. An A-star candidate never skips writing down this unsimplified substitution step because doing it entirely in your calculator will cost you the method mark.
So what does that numerical value actually represent? It gives you exact geometric area. Definite integration allows you to find the exact area trapped between a nonlinear curve and the coordinate axes. You will learn to evaluate these regions perfectly, finding shapes that would be impossible to measure with standard geometry. But you must beware the x-axis. Areas that lie below the x-axis evaluate to negative definite integrals. If your region crosses the axis, you cannot integrate from the start to the end in one go. You must find the roots, split the integral into distinct sections, and take the absolute value of the negative portion.
Finally, we combine your new calculus skills with coordinate geometry. You will calculate the area of complex regions trapped between a curve and a straight line, or even between multiple intersecting curves. This often requires you to use simultaneous equations just to find your starting boundaries. Then, we take these two-dimensional areas and rotate them full circle around an axis, generating three-dimensional solids. You will use a specialized formula involving pi to find the exact volume of revolution for these shapes, reliably securing the final, most demanding marks of your exam paper.
Integration transitions you from abstract algebraic manipulation to tangible, complex geometric problems. You will reverse differentiation, evaluate definite integrals with strict limit substitutions, and calculate exact areas and volumes of revolution. Remember, the word exact in your exam is a strict instruction. It means no decimal approximations. Your final answers must be left as integers, fractions, or in surd form. You have the algebraic tools. Now let us build the calculus.